All right, concentration. So concentration is a major mathematical feature of this chapter. We have to be able to recognize the amount of solute in the solvent. And there's two ways to do that. We can think of things as dilute or concentrated, weak versus strong, whether it's alcohol, whether it's vinegar, whether it's some kind of sweet tea versus semi-sweet tea versus unsweet tea. We need to have a handle on what does it mean when you have a solution. How do we compare it to other solutions? How do we use it in a reaction? The two types of concepts we cover in this video will be molarity and percent composition. Molarity is based on moles. Notice the first three letters, MOL. The reality of molarity, though, is only chemists use moles, and most of the rest of the world doesn't. That's the reality of all these chapters that we've used concerning moles. They're very useful for chemistry, but not useful for anybody else, because the chance of carrying around a periodic table in your pocket for the rest of your life to deal with moles is unrealistic and unlikely. Most of the rest of the world uses percent composition because taking mass to mass or volume to volume or mass to volume is very easy and can be done anywhere at any time. So we'll talk about both, definitely percentage being the easier one of the two, and that's why most of the rest of the world uses it. But we'll focus on molarity a little bit because it ties very well into our grams and moles from our solids chapter last week, and it'll tie into our gases and liters and moles in our chapter and final chapter next week. So as we look at molarity, realize that it has a definition of moles per liter. But very similarly, we could cheat and say, well, that's just moles per 1,000 milliliters if we want to do the metric conversion right away and not have to prove it or show it. Because of there being 1,000 milliliters in 1 liter, that would be an equivalent conversion. So it turns out we'll probably use this one more often than not. And molarity itself for us is really just capital M. We've seen capital M on bottles all semester long. The larger the capital M, the more concentrated the solution happens to be. And in this chapter, we're going to teach you how to find capital M, how to use capital M as a conversion. But recognize this idea here is just one more conversion in our little toolbox of conversions. We're just adding a new definition. So we have definitions like Avogadro's number equals a mole. We have periodic table grams equal a mole. We have subscripts and coefficients equal moles. And now we have moles of solute per liter of solution. So remember, solute, that's the little guy. And solution, that's the whole. So really this is just a piece divided by the whole concept, like a percentage, but using moles in the periodic table. We'll do percentages separately and later. So this gives us our third way to get moles. So we can use mass on the periodic table. So remember that comes straight off the periodic table. We can cancel moles. We can cancel grams. We did that quite a bit in our previous homework. If we have atoms or particles, we can cancel those. If we have moles and want to get to particles, we can cancel those. But now we see that if we have liters, or maybe 1,000 milliliters instead, we can cancel liters and get to moles, or we can cancel moles and get to liters. So as long as whatever we have cancels, it's really no different than our last two chapters. And that'll summarize basically the theme for Exam 5 in Intro Chem. One of the things that we're going to look for in this chapter is writing down volumes, writing down molarities, just remembering that molarity is a conversion. The problem that you'll notice, though, is it's just capital M. So when you see molarity and you think molarity, remember it's just capital M, but that really means whatever number moles per 1 liter or 1,000 milliliters. Might be a little bit more handy. So notice when we look at this problem, There's two numbers now and not one. That makes this chapter a little bit tougher because which one do you use and put out front? But I'll remind you that this is a number. It's a measurement with a unit. Capital M is a conversion of moles per liter or moles per 1,000 milliliters if you want to go ahead and do the metric conversion. So this is not really a number. It's a conversion, just like density was a conversion. So understanding that's going to make the homework go a whole lot faster, realizing that these numbers never go out front. These types of numbers do. Measurements go out front. Conversions go in the middle. Conversions from the periodic table, conversions from balanced coefficients, from subscripts, from Avogadro's number. Those are the things that go in parentheses. These kinds of numbers are the ones that are going to go out front. So we're going to put 200 mils out front. And then much like previous chapters, we're going to get rid of milliliters straight away. If we realize that's what this number really does for us, that's just 1 mole per 1,000 milliliters of solution, or 1 liter. We're just saving ourselves that metric step. And then if we want grams, we're going to do one more conversion from the periodic table and say, well, we know that in 1 mole of anything, we can go to the periodic table and get grams, in this case of NaCl. Sodium happens to be about 23, and then chlorine about 35.45, based on the periodic table that I have here next to me. So that's going to be a 23, so Na plus Cl goes here from the periodic table. So that's a 23 and a 35, so that's about 58.45, thereabouts. So notice not a whole lot different. You're canceling now milliliters instead of grams from our last chapter. So notice they show us the metric conversion in their example, and they did it over 2 steps. I like to put it all together. Less buttons to hit in the calculator if we just jump ahead and do the 1,000 milliliter conversion straight away. And then times it by that 58.45 kind of number that we came up with from the periodic table, which should be Na plus Cl. Most importantly, notice what happens here is milliliters cancel. We wouldn't really even have the liters at this point. We would have skipped that part. Moles cancel, and then grams are left, and that's exactly what we want. So the reason molarity is important for chemists is this is how we know how to make a solution. So let's pretend that we have lab coming up that needs a solution of sodium chloride. The lab calls for 1.500 capital M solutions to be needed to have a successful experiment. We want to know how much would provide us with 100 grams of salt if we were to, say, evaporate all of that sodium chloride. So if we evaporate the water, sodium chloride would be left, so to speak. So notice in this situation we have 2 numbers again. So which number do we use first? Well, if you realize that this is a number, it's a measurement, this is a conversion. That's different. This is the kind of number that goes out front. It has 100 grams of sodium chloride that we want. We're going to get rid of grams of sodium chloride by putting it on the bottom. We go to our definitions of moles, and one of them is every mole of sodium chloride can be measured on the periodic table, and that's just Na plus Cl again from the periodic table. So 23 plus 35 is about 58.45. Moles will then cancel. So in moles now to milliliters that they want, this is where we can use 1,000 milliliters if we use capital M for moles. And this happens to be 1.500. And then we keep milliliters of the solution left over. So really this is just the exact same problem backwards. In the previous problem we went from milliliters to grams, now we're going from grams to milliliters, and that's just flipping over every single conversion that we had on the previous example. Notice the importance of what we did though is no different than the last two chapters. Grams have to cancel first, moles have to cancel next. We didn't even use liters, we just went straight to 1,000 milliliters. So cut to the chase. So when I make solutions, just about every week for Intro Chem, we have to deal with this same process. So whether me or a work study or other chemistry teachers have to deal with this. So what does it really mean to make a solution then? Well, much like our aspirin lab, we have to weigh some powder on the balance. We need to know how much, that's stoichiometry. If we know how much, we can put it into water and then dilute it to some volume. And that'll tell us, based on grams, we can go to moles, based on the periodic table. And then we can look at volume of the solution, and that's just moles over volume of solution. That's molarity. That's the capital M that we put on that bottle when we're done. So this problem's going to look very similar to what we just did about 2 problems ago. We have 2 numbers. We need to know which one to put out front and which one to do first. So as we're looking at these, just remember that even though it looks like we have 2 numbers, here's your number. This is really moles per liter, or 1,000 milliliters. That's a conversion, not a number. So it's this measurement number, grams or milliliters typically, that goes out front. And whatever value we have, whatever measurement we have, the theme in the last 2 chapters and now 3 chapters in a row, and it'll continue to be 4 chapters next week, get rid of those units of milliliters. To get rid of milliliters in this case, we're going to say that, well, it is moles per liter, but it's also moles per 1,000 milliliters. So we can say in 1,000 milliliters, which is 1 liter, we can use capital M, 0.15 moles. So capital M always changes. It's not like a 1 mole to the periodic table or a 1 mole to Avogadro number kind of conversion. It's specific to whatever capital M says. What's not specific is this value here. It's always 1 liter, or it's always 1,000 milliliters. That cannot change. In this situation, we're trying to prepare the solution, so bottles don't measure moles on the balance, so we need to go one step further and go to grams. So if we continue to get rid of moles and go to grams, that's just the conversion from last week. In 1 mole, we have Na plus Cl on the periodic table. We've seen that a few times already. That's 23 for sodium, and it's another 35, so it's about 58.45 roughly. This will tell us how many grams to add. And in this case, that's going to be 4.48 grams. So we're going to measure 4.48 grams onto a piece of wax paper that's on top of a balance. That balance is going to say 4.4 grams. We're going to take that powder and put it into a flask. That flask will measure, in this case, 500 mils. So once we put in our 4.4 grams down here, all we're going to do next is fill this up with water. And then when we're done, we're going to put a label on it that says, in this case, 0.15 M. And then we're going to use it in class. So I do this all the time because it's a stockroom full of powders. And I take the powder, I know its weight based on the periodic table. I know how much solution I'm going to need for lab, so I can calculate exactly the concentration I need to do those experiments quickly and safely, and not have something that's too strong or too weak to get those observations that we want. A little bit faster way of doing the exact same thing is using dilution. Dilution, though, assumes that you already have a solution that's too strong, and you're just going to make it weaker. It's no different than having a child makes sweet tea or Kool-Aid and it's being way too sweet, the parent isn't going to dump it out, they're just going to add more water, they're going to dilute it. This formula tells us exactly how to calculate that end result. So it's typically written as M1V1 equals M2V2. So in these kinds of situations, you're going to get 3 of these values, and then you're going to be solving for the 4th. So these problems are pretty straightforward because one of these is going to be like x in algebra, and then you just solve for it. So let's try one. Notice what we have here is 2 numbers together, and then 1 number by itself. That just means that here's your V1 and your M1. Here's your M2, and volume is your V2 that is missing. So as long as you keep those numbers that are together in the problem, this one's pretty quick. So if M1 V1 equals M2 V2, let's take 0.15 capital M, its volume of 500 milliliters. That's going to equal the new concentration of 0.50 M that we have to dilute. We're just saying how much do we need to dilute. So it's basically saying from our strong bottle, how much do we take out, dilute to 500 mils to get 0.15. The next step we're going to do here to get rid of 0.50 is to divide by it. In algebra, the units are going to cancel, but the number also cancels and makes 1. So that gives us V2 by itself, which is what we want. In algebra, what you do to one side, you have to do to the other. So 0.50 M over here, molarity cancels, milliliters are left. And that's exactly what we want. So this tells us we have 150 milliliters of solution needed. So in real life, what does that mean? That means that if we have this bottle in the stockroom that says 0.50, we're going to take out in a graduated cylinder 150 mils based on this calculation. And then we're going to take that 150 mils and put it into a new flask that's much bigger. And once it goes in, it's going to be down here, 150 mils. And this calculation tells us that we want 500 mils total. So we're going to dilute up here to the mark, which says 500 mils. The rest of this is just going to be water. And when we're done, then we can label it this new concentration of 0.15 because we know that value before we ever started. So all we're doing is taking a bottle that is really strong, really concentrated, and making it very weak. Just like sweet tea, and adding water to dilute it down and to make it seem less sweet. So like all dilution processes, add a bunch of water. But in chemistry, we care about how much water, and that's what that calculation is good for. So molarity you'll see in the homework a little bit with dilution. It'll typically say the word diluted either in the answers or the question itself. So those are always pretty recognizable. But in many cases, there's going to be 3 numbers, not the 2 that we've seen in the previous problems. And that'll tell us that we're going to need to solve for that missing 4th. So we'll come back in a separate video, talk about percent compositions, and then we'll wrap up moles one more time with some stoichiometry from balanced chemical equations. Catch you next time.